All right, I'm a little early, but I'm just going to check the mic, make sure everything is running, and then I'll wait a minute. All right, so I'm maybe going a minute early, but the thing is saving everything. So I know it says 11:59, but okay, so let me answer a question in the room, so to speak, and that is this word of the day thing and why I'm doing it and everything like that. So of course, oh, I'm getting the let me cut the volume down. Okay, so um, so the first thing is that is if you log in with syncing or you have already logged into a Google account, when you come to this page, it's going to have this with your Google account. You don't have to do that. That's not a big deal. You can use this on any computer. It's just this, if you want to get save a copy to your Google account of your response, that's fine. Now you're going to get an email back with your response anyway, so I don't think it's that important per se. But fill out this form. It's pretty simple. What you do is give it a second. Oh, it opened a second one here. To that one. So all you do is in this block, you put your email, and then whatever the word of the day you hear is what you put there. Now, I'm starting the lecture off with the word of the day, but the point is the word of the day is going to be randomly placed in the lecture along the way. So I'll just stop about 30 seconds and I'll say, hey, the word of the day is, and today we'll just make it nuts. Okay. So, and we know how to feel, we know how that feels. So, hey, let's go back. So how do you do it? Well, you just put in, I'm going to put in John Doe at ATU. Now, you want to put in your own email. Now, here I should put in, let me put in this, or Fithin at ATU. And it doesn't matter whether it's capital or not. And I'll talk about that in a second. And then I'll hit submit. And then there you go. It's submitted. And I can edit my results. If I go to my email, which I don't think I have my email up, but if I did go to my email, let me just see. I should receive an email response back. Oh, I hope I don't have to do that duo thing. My machine is a little slow today. I may have installed something on it that made it slow. I have no idea. Or it may just be the general state of computers. Okay, so here's what I got back. An external sender. Fluid's word of the day is, hello computer. You can do it. You can do it. Or maybe you can't do it. Okay, so there it is. That's what I entered. Now, what do I see on my end? I'm just going to show you this because this is not critical for anything, but if you go down, I've made the Google form here. There's the thing. I don't even know if this little header came up or not. I don't think it did. So give it a second. So already we've got 11 responses. Here they all are. So what I'm going to do, okay, and this is not, again, critical. It will save them in this spreadsheet. That is a Google sheet. I have written codes before to harvest data out of here. And so what happens is, and there I am, but you see I typed in the nuts with a wrong case, but I just changed the cases and I basically pull this information out. And that's how I'm going to give extra credit. Now, there is one thing we need to be aware of, and that is our, okay, I may have to wait for it. No, it's there. Okay. So let's say today is Friday. Well, that's because that's what today is. And then you got Saturday, and then you got Sunday, and then Monday. So we're going to reconvene on Monday. We're here right now. So today, it's nuts. It'll probably be nuts every single day the rest of the semester, but we'll start changing our word for each day. So if, say, someone comes in and watches the lecture on Saturday, and they type in nuts, that's fine. I'm going to give more credit to people who are entering it earlier. So there'll be more credit for people who watch it live and less credit as you go down in time. To the point where when it becomes Monday, when you watch Monday's lecture, at the end of Monday's lecture, there'll be a new word, some new word that they're entering. So if you watch Friday's lecture after the time for Monday's lecture, you're not going to get any credit. The reason being is because, as you saw in that spreadsheet, your name will be associated with this new word and this old word, and the timestamp will be after Monday. So it'll be looking for the new word from the timestamp of after Monday. And so you'll get credit for watching them and staying in sync, but no credit if you fall behind. And that's just because it doesn't make sense, first of all, and programming, for my perspective, to make the program do that, it's a waste of time. So I'll just do this, I'll harvest these, and at a certain point in the end of the, maybe middle of the semester, I'll run the first draft and email you your word of the day and when you executed it and stuff like that. So let's get into fluids now. Okay, and we're right here. So now week 1 was the units. So I'm going after week 2 and probably week 3, and I'm going to go straight down to let it come up. I'm moving kind of slow. I'm going to go straight down to the assignment and then pick it up. I may actually download it and put it there. I'm not sure yet. Okay, so this actually has to do a little bit with units as well. So let's talk about some of these. Give me a second. I'm just going to save it, and then I'm going to do show all, and then I'm going to pop it open. Oh, why does it do that? Pops it back open in this. Show in folder. Now pop it open. All right. So let's go ahead and drop the one from the last class period. So it says, and sorry for the quality of these. I just sort of snapped them and put them in here. So it says the pressure difference across the partial blocked artery is approximated by this, where V is the blood velocity, this is the viscosity, this is the density. I'm glad that he put them in here. The diameter, the area, and area. So then he said, would this equation, okay, determine the dimensions of this constant and this constant. So first we can just look right here. First of all, look at the left side. This has got to be in pounds. Let's just say pounds per square inch, which we should be thinking more along the lines of force per unit area. So that's what would exist right here. What would exist right here? So let's look at this and say we've got the K. I can't tell. I think that's a V. And this is the viscosity, this is the velocity, and this is the diameter. So if I look at the units here, he said the blood viscosity is F, L, I'm getting that right here, to the minus 2 T, and then, okay, that's the viscosity, so that's this one. The velocity, which I don't really even need it, so it's in feet per second. Remember, this is the length, so you got force, length, and time. Or you all can also have a mass. So diameter, that's just length. Okay, so this length will cancel that length. Oh, this time will cancel that time. Oh, wait a minute. So let's look real close here. So what I get left is this. And that is the same thing as is on the left side. So therefore, kV has no units. This happens a lot in fluid mechanics. The reason it happens a lot is because two reasons. One, naturally it came out that way. And then the second thing is, if it had units, then you would have a kV in SI that would be one value, and then in British gravitational would be some other value that you'd have to have in this equation. Well, you know, this kV for this unit's this and this. Believe it or not, kV is the same no matter what unit you're using. And that's one of the beauties of this, is that when you see in fluid mechanics, they love to, and in heat transfer as well, especially convective heat transfer, they love to find constants which have no units. And the answer to that question would be obvious. Would this equation be valid in any system of units? Well, it would if these were unitless. And therefore, that's what happens. Now, okay. So, let's go down here and look at this, okay? If this is velocity, this is the length, and this is the kinematic viscosity. Now, I'm going to go back to the book in a second and show you something interesting. Having the dimensions of this, which of the following combinations are dimensionless? Okay, first of all, the way I always remember this, if you're in a pinch and you don't have anything to look at, I remember the equation looks like this. This is a standard equation, which is the stress is equal to viscosity times the strain rate. It is, again, similar to, and here, it depends on what the symbol you use. This is modulus elasticity, fulfills a similar role. This is the strain, and this is the strain rate. So this relationship is the same, actually. And if you get in a continuum mechanics course, you'll see them representing it that way. Now, what are the units here? Over here, it's pounds per, I'm going to use this, say what's the units? Well, this is the velocity over a distance. So feet are, since I used inches over there, inches per second per inch. Okay, that's the distance here. So in other words, it's like mu change in velocity over change in like the height. So this is units length, this is units velocity. So this cancels that, and so you get pounds second inches squared, or you get a force, a time, a length to the minus 2, and I wrote 1, but I should have written 2. Now, if you look up here, he says kinematic viscosity. Wait a minute here. Okay, so if you look at this real quick, you're like, okay, he already talked about viscosity. This is something called dynamic viscosity, which is written this way. I like this one more than the other, but how are they related? Okay, I'm not good at writing this symbol, but to me it kind of looks like that is equal to this over the density. That's all there is to it. Now, let's see if we can get the units out of it to match that he is stating, just to make sure that I believe that he's right. Okay, so let's take the units, and we're going to basically put them in units. F, T, L to the minus 2. Where's that come from? It came from right here. And then over the density, which is mass per unit volume. And the first thing that should flag you right off is this. What happened here? I don't know what happened. Okay, this should flag you immediately. I've got a force and a mass together. That's a big no-no. You should not have that. Okay, so let's see if we can get rid of that. How do we get rid of it? F is equal to ma. This is the converter from a mass to a force. You should think that way too, because you got this thing. Well, if it's a pound mass and a pound force, what, but this is something that you should think. Okay, a force is equal to a mass feet per second squared. Okay, so if I want to get rid of the force here, I can put this in and replace it there. So let's see if I can do that. M L T to the minus 2, I'm putting that in. Then I've got my T, then I got my L to the minus 2, then I got my M down here, and then I got the L to the, so what I'm doing is copying these are going right here. So what do I get? Bang, bang. Okay, so what's going to happen here? Okay, one of these is going to take this down to a minus 1. Got a length here. So I got a length that's going to, okay. So here's what I'm going to do. I'm going to slide to the right now, and I'm going to basically put everything, I'm putting a plus sign, but be patient with me because I'm trying not to make a mistake here. If it's minus 3, move it to the top, it becomes plus 3. Okay, so what do I see? I see that I have a length in this one. This will knock it out, so I'll get an L to the plus 1, and so I'll get L 2 T minus 1. Is that what he had? L, okay. Whoa, that's weird. Okay. So yes, that's what he had. L2 T to the minus 1. So again, I'm just checking this. I haven't even answered the question yet. So there it takes you through the process of, and I think that's instructive because this is an issue that comes up all the time. Mass and force never exist together. You've got to either pick one over the other. And in this case, I got rid of one, I reduced it down, and I got this unit out of it. Now, the question is, what is non-dimensional here? At this point, let's see, what can I do? Can I just select all of them? Or do I have to, here, just select them all and go back. I'll hit the delete. Now I'll go back to the problem itself. And I'll say to myself, okay, what is non-dimensional? How about V times L times this weird viscosity symbol? Well, what do I get? Units. Feet per second times the length, because that's what that is, times length squared T to the minus 1. Okay, all you're doing is summing your subscripts. Uh-oh, I immediately see a problem. The answer is no, that's dimensional. This one I have hopes for. So let's look at the second one. V L over viscosity. This one I have hopes for. L T to the minus 1. Then I got an L. And then L squared T. Oh, yes. And believe it or not, that is what's called the Reynolds number. It's written usually in two ways. Reynolds number, which is non-dimensional, rho, velocity, diameter, or a length thing over mu. This is for pipes. So this will be some sort of length thing. That's the velocity. That's the density. That is the viscosity, but it is not the kinematic. It's the dynamic. Now, what's interesting is, let's see how did this become Reynolds number? So you're looking at this and saying, what? That and that are Reynolds number? Well, given the fact that this, again, I'm awful at writing that symbol. Okay, curves back a little bit to the left. Okay, and then this is mu over rho. So look right here. It's a velocity times some sort of length, diameter of a pipe or some sort of length, over that term right there, which is in fact what that is. So usually in Reynolds number, this one is open in the sense that it could be the diameter of the pipe, it could be the wetted length. It's got to be a length reference. And for aerospace, it might be the length of the aircraft, the chord length, things like that. Thing is it might be different based upon what it's describing. The key is it is non-dimensional, and it turns out through physics, this means I can take a small, 6-foot section of a Boeing 747 that's 6 foot long and put it in the wind tunnel and blow air over it or suck air over it at a certain speed of velocity, say 100 feet per second or something. Then, from the viscosity of the air, whatever length I've chosen, which a lot of times for wings it's going to be a chord length, but it might be some other length, characteristic length, which is what they're usually called, characteristic length. I can get a Reynolds number, rho, velocity, whatever length thing that my characteristic length that I have chosen, and then I can get my data, take all my data, plot all my data against Reynolds number, whatever the data might look like, whatever I'm putting, and then I go back to a real aircraft that's maybe, 150 foot long. I don't know how long they are. I'm just making this up. So it's 150 foot long. The Reynolds number now applies to that. So if I'm getting the lift or the drag or something like that out of this, and I get, 10 pounds or something, just making it up, and I want to find out the lift on the real aircraft, I scale the lift by the Reynolds number. And then suddenly I find the Reynolds number over here, I'll work my way through it, and I'll get the lift or the drag or whatever on the real aircraft. Why? Because I can scale it through the Reynolds number. And the Reynolds number, this is the first appearance of the Reynolds number in this book, in the problem sets. So there you go. Now let's get rid of all this stuff, and let's see if I can make room for the next. Okay, I may not have, I didn't make it down through the whole thing. Okay, here we go. Okay, so now, what do you think about this one? Let's see, this one and this one. I'm not holding up too much hope here now because, one, if this is non-dimensional, without that length, I don't think that's, but let's try it out. Okay, feet, okay, now, there I go. The velocity is in feet, or a length, per second. The kinematic viscosity is length squared time to the -1. Now, this was squared, which means effectively it is this times, see, the problem is I can't get this down to f to the 0, length to 0, time to 0. That's non-dimensional in that there's no dimensions there. Can't get it. Now let's try this one. Velocity over length, and then this viscosity. So feet per second over length, whatever that length is, times this. Oops, mistake. This coming from here. Well, it's good for that. It's not good for that. So, it has force, no units there. It has length, -2, and it has time, 0. So, Boom. Not a 0. So the answer to this one is that, yes, this is the Reynolds number, and it is the only one that is non-dimensional there. So here, I'm going to leave this one up to you. It's the same thing. Now he's asking you, what are the dimensions in the MLT system? That should say MLT representation. Okay, I know I'm being ridiculous on that, but it's not an MLT system. The density in an MLT system is kilograms per meter squared. That is an MLT system. An FLT system is slugs per feet squared. So that's in an FLT system, but it is written as an MLT representation, meaning there is a mass sitting on, and sorry, mistake, I hope that didn't distract you from what I'm trying to say, which is, it's a third power, which in fact is the mass per unit volume. Regardless, that's the definition of this, the mass per unit volume. You don't write it that way in an FLT system. You write it as a representation. So I'm sorry I'm being ridiculous about it, but that is incorrect, and it's never been corrected in the book. And so don't get these confused in what a system is and a representation. The book is misrepresenting it. So an MLT system, let's look at it. An MLT representation. Let's look at this. Okay. So what do I have? I have feet per square inch, pounds per square inch. So a force per unit area over a mass per unit volume. Now, if I want to go forward, I can do this. L to the minus 2, M to the minus 1, L to the 3, and now I can have F, M to the minus 1, L to the 1. Big problem now. I have an F and an M together. Not good. So what do? F is equal to MA. M, acceleration is length. This is acceleration. Feet per second squared, for example. Now I'm going to move the M over. Well, wait a second. I want it in the MLT system. So in other words, I take this and put it right here. And then I have, for that F, I have M, L, T, minus 2, M, minus 1, L. Okay, then I just copied that down, and I copied this down, and this came from the F. So now you can see I get M to the 0th power, L to the 2th power, and time to the minus T. So there's your MLT thing, the pressure over the density. And what is interesting is this would be the same units as V squared. Now, it's not so surprising that this is the case, because later we'll learn Bernoulli's equation has this in it. Okay, and this comes from, and we'll find out later, this becomes from a well, we'll talk about that a little bit later, but we're just going to talk about the units. If you have a Bernoulli's equation which lists this way, so there's another term here which it's not part of the discussion. If you have these two terms in an equation, they have to have the same units. So later on you'll see this. So what do you have on the left here? You have force, like PSI, pounds per square inch. What do you have on the other one? You have some other term, which is mass per unit volume times feet per second, feet squared per second squared. Why? Because this is foot per second, and you square it. Now you look at it again. First thing you should see is you should get upset because you have these two tied together. Now, what do you want to do? Well, since this thing is written and has the basic units of PSI, for example, I would prefer to leave the force and convert the mass this time. So again, F is equal to mass times acceleration, or mass, convert this around, is equal to force, length to the minus 1, t squared. I'm going to inject that in here. If I inject it in here, F, L to the minus 1, t squared, and then just take these, and I'm not even going to convert them yet. I'm just going to say L to the minus 3, L squared, t to the minus 2. Now, I start looking at this. What do I get? F, L, t. Okay, I have one of those. How many L's do I have? So you just add this up. This plus that plus that. So you get minus 4, take away 2, and you get minus 2. T, oh, this is lucky. I get nothing there. So what do I match? I match the same thing. So the units of rho, v squared over 2, are pressure. So in fact, even though the units may confuse you at first, they do exactly match. They're the same thing. Whoa, okay. So you can go through the rest of these, but you get the point. I only did this one, and then I got myself distracted. Here's the first thing. You can look at that one, and you can tell the answer right off. I've kind of answered C by describing the fact that this pressure and rho v squared are the same units. So that should tell you right here there shouldn't be any units out of this. This one, yeah, there's going to be some kind of unit. And yeah, this one's going to be some kind of unit. Oh, that's it. I don't think there's any more there. Let me see if I can make my way back to where I was. Okay. All right, so this is the first part. It's still dealing with units, but let me see if I can get back. Okay. I have to remember which one that was. It's got to have been this one. I mean, the one right before this one. So I'm going to jump into this one. I'm going to, if you don't mind, I should have eaten something, but I'm going to eat a bar real quick. Okay, I'm going to apologize because I gave you way too many lectures. And here I am doing it to you again. Let's look at homework 3. I'm going to download it. Apparently I've got to open it a different way. Okay, so I'm going to drop. Did I do it twice? I did. All right. This one has, I don't know, 4 pages. This one's kind of straightforward. But before I do this, let me go back to here. and reiterate my apology. Um, I produce a lot of these lectures. One of the things that's so nice about it, you can hit the speed button on here and listen to it super fast. The live lectures, you can't do that. But you can listen to the live lectures after the lecture completed and then pick it up in higher speed that way too, which is partly why I'll still allow people to get credit as long as they do that before the next, they're getting extra credit as long as they do that before the next class period meets. So again, there's way more lecture material than there should be here. I mean, here, this is 29 minutes, 31, 20. I mean, that's there at least 12. And this one's 9. So the last two are reasonable. 2, not so much. Okay, everything's moving slowly here. So let's get back to the problem. So basically it says 1 cup of cream has a density of 1,005 kilograms per meter to the third. It's turned into, okay, I'm sorry, 1 cup is turned into 3 cups. So, you can look at it kind of like this. Well, I didn't change the mass, but I did change the volume by 3. So I took something that was, whatever that volume is, and the mass, and then, did I go to 3? I went to 3. So suddenly I did it like that. So I would argue that here we'll do this, 1,005 over 1 cup. And now you've turned it into 3. So you took the mass, so you dropped the density. I mean, you dropped the density so that it became much lighter. So I don't think I put the answers in these. Maybe I did. I should have. I don't know why I didn't. Okay, a can of pop indicates that the can contains that. The mass of the top, the whole thing is that. And the empty can weighs that. Determine the specific weight, density, and of the pop, and compare your results to, I'm assuming, see now this part, I really don't know. Is he wanting us to include the empty can? But he says, oh, the can of pop. Ah, okay. The mass of the full can of pop is that. The can of pop contains 355 milliliters. The mass of the full can of pop is 0.369. This is bizarre. While the empty can weighs, so the weight of the empty can is 0.153 newtons. Okay, now here's your deal. I'm going to assume G is equal to 9.81, and the weight of the can is equal to the mass of the can times 9.81, which means the mass of the can would equal to that, what, 0.153 newtons divided by 9.81. Then you'd take that, that's the mass of the can, the aluminum part of the can. The mass of a full can of pop is that. So whatever that would be, I would take the mass of the pop only would be the mass of the full can of pops, 0.369, minus the mass of the can, which, I don't know, I'll take that to be 0.02 because maybe it's, that's not right, but I'll just say that. And so the mass of the pop only, because, well, here, I'll break out my calculator. Okay. 0.153 divided by 9.81, 0.015, okay, minus 0.369. And so the mass of the pop only is equal to 0.353. And let's see, where's the volume? It indicates it contains 0.355 mass per unit volume, 0.353. This would be kilograms, and this would be no, 355. Now, what you'd want to do is convert this to meters, cubic meters, and that'll give you your density. Now, specific weight, okay, so whatever number that is, then say you got a number here. So I'm just going to say convert that to cubic meters, meters cubed. Then you get a number. You want specific gravity. Here, let's do specific weight first. Rho times G is equal to that number times 9.81. And this will come out as newtons per meter cubed. And then if you want specific gravity, you either take this number of pop and divide it by the density of H2O at 4 degrees C, and that'll give you your specific gravity. And that's all he wants. So let's say density of a jet fuel, 775 kilograms cubic meter. Well, I know the density of water at that H2O at 4 degrees C is defined as 1,000. So that's where we got some of our units in SI from. Specific gravity. Well, that's easy enough. 0.775. Why? Density of the jet fuel over density of water at 4 degrees C. You could go on and say, now I want to know specific gravity in pounds per cubic foot. Now, what might happen to you is you might say, I want to convert kilograms to slugs and things like that. Or you might say, okay, it's nothing more than rho G. G is 32.2, and rho is nothing more than rho of the jet fuel, which is nothing more than rho of H2O at 4 degrees C. Well, here, let me do it this way. What is rho of the jet fuel in those units? Well, specific gravity times 1.94 slugs per cubic foot. If you look in the thing, that's where he says that's the density of water at 4 degrees C, but it's in these units. So you take that 0.775 and you multiply it times that, quickly gives you back the density of jet fuel equaling to let's see, 0.775 times 1.94, 1.5035, and this is debatable digits, so I'll remove them. So the key is I changed units by using a unitless number. Specific gravity, no units. So I used the specific gravity, which has no units, turned around and put it right here because it had no units. The units came from this density, and I can now put this jet fuel in there, and I can multiply 32.2 times 1.5, 48, about roughly 48 pounds per cubic foot, which would be the same thing, and that's gamma of the jet fuel. Okay, if I want to know gamma of the jet fuel, I would use specific gravity times gamma of water at 4 degrees C. That number, 62.4 times 0.775, I think it was. And I get 48.36, have a few more digits here. Still debatable whether you could even report those digits. And so the key is, again, non-dimensional numbers can be used in either or any coordinate system. So that wasn't part of the problem, but I thought I would add that right here. I think, no, there is one more. Tank of oil has 25 slugs. Determine the weight in pounds newton of the Earth's surfaces. Now, wait a minute. Oh, it has a mass. This is silly. Okay. 25 slugs times G is equal to 25 times 32.2, and that'd give you the weight. Now, let's see, what would be the mass in slugs and its weight in pounds if it's located in the moon where the gravitational attraction is 1/6 divided by 6, and that's going to be your number. And that's it. So we got 2 minutes left. Let me bounce back. So that covers week 2 and 3 homework. Let's see. Content. I will need to go and look and see where everybody is, but I think this week I'll start opening weeks down the road a little bit. I don't have week 6 open, so I'm going to go through all the courses and open the next week. What we'll do on Monday is start in on, we got to do viscosity. That shouldn't take a week. So we need to move a little quicker, I think, but so I don't know what that is. There's video that's. So on Monday, let's see, I'm going to try to be there, but if you want to pick up the live stream, I'm going to try to bring my Surface and try to figure out some way to cast it onto the wall, which may mean that you might get a better experience picking up the live stream than you would being there. It's up to you, whatever you want to do. But I'll send you an email this weekend I'll send you an email with the postings of the of where the live streams are picked up at, and we'll just go on from there. So with that, I think I'm done.